Hello everyone, I'm Mr. Song. I'm teaching AP Statistics. Today we have chapter 1, section 1.3. What do we learn today? When a distribution function is given, we need to describe it in AP test. So we need to show center. So what do we need to use to describe the center? Mean, median, and mode. So how about spread? Spread of the distribution. So we use range, standard deviation, and interquartile range. We also need to show the extreme values. They are outliers. We have a very nice tool to show the picture of the distribution, and that is a box plot. And box plot uses 5 numbers. Okay, before we get deeper into statistics, I would like to show you the overall picture of statistics. We need to know population. However, it takes a lot of money and time, so we pick only part of the population, and that is a sample. So we know this sample. So based on the data of the sample, we estimate population using mathematics. The specific tool of the mathematics is probability. So this mathematical process of finding population based on sample is called statistics. So population, this is our target. So we are using sample instead to save money and time. So observations. So let me give you an example to know the difference between the sample and observations. Let's just say there are 1 million AP Stat students. Okay. So we want to know what their scores are before they take a real AP test, so mock test or fake test. But we cannot give 1 million students an AP test. So just to pick 1,000 students out of 1 million. And these 1,000 students are observations. So 1,000 students, 1,000 observations make one sample. So we could give a second mock test, the second test. So we take these students back into the population. We pick another 1,000 students. That is a second sample. So sample. So this is sample 1 and this is sample 2. So we already have one sample with 1,000 students. We take the second sample with another 1,000 students. So notice that we use 1,000 observations and 1,000 students all together make one number. That is the second sample. So number of samples, there are two samples. However, observations for each sample is 1,000. They are completely different. Number of observations and number of samples, they are completely different. We need to have a clear understanding about the definitions of sample, number of samples, and number of observations. Number of observations is also called sample size. So number of samples and sample size are totally different. And most of the stat formulas have sample size in it. We clearly understand what it means. Okay. When we pick samples, there are 2 different ways. The first one is sample with a replacement. Okay. We have 1,000 observations, but we pick one at a time. So we pick one student, and we have a test. We give this person test and put it back. And then we pick a second person, and then we give a test. So we pick one observation at a time and bring it back. That is a sample with the replacement. The purpose of replacement is we don't want to change the population. We bring this sample back into the population so that population does not change, and math becomes very simple because we don't change the population. So math is accurate and simple compared to sample without replacement. Since we check one observation every time and we bring it back to the population, and it takes a lot of time and money. So sample with replacement, it has good Simple mathematics, however, it takes time and money, so that it's convenient to take 1,000 students out of population at the same time. And then we give 1,000 tests to 1,000 students at the same time. That is a sample without replacement. So we do not include the previous observation for the second one. So sample without replacement, and it is less expensive because we can do it right away at the same time. So it's less expensive, we save time and money. However, we change the population, and math is more complicated than sample with replacement. So AP test, we will use this mathematics only because it's complicated. And if you have a sample without replacement, we will approximate it. And then we still use a sample with the replacement mathematics. We'll get deeper into it. So next, I would like to show you the clear comparison between population and sample. So population, there is one population. Therefore, so everything in this population is a fixed, constant. So sample size, big N, let's just say there are 1 million students. So there are 1 million students, and we want to know their AP scores. So we checked their scores. The first person, so AP score ranges from 0 through 5. Okay. First student got, let's say, 4. The second student, 3. And 5, 0, ... And we have 1 million students. Okay. Divided by 1 million. 1 million. Then it becomes population mean. The symbol we use for population mean is mu. Okay. And this is the convention that we almost always use in AP statistics textbooks. So population variance is sigma squared, and definition is like this. So let's just say population mean is 3. So mu is 3. And then the first student got 4. Okay. Then 4 minus 1, which is 1, and 1 squared. The second student got 3. So 3 minus 3, and 0, and 0 squared. So next student 5, and so this is 0. Let's say this is 0. Then 0 minus 3, which is negative 3, and then we square it. So there are 1 million terms in the numerator, and then we divide it by 1 million. So this is population variance. We squared the deviation, so this difference is called a deviation. We squared it so that negative deviation becomes a positive. That's the purpose of squaring each term. And this is mathematical notation with a sigma. So how about the standard deviation? Sigma, simply we have a square root over population variance. Since we squared the deviation, it got exaggerated, and we want to bring it down to the original value. So we have a square root, we square it, and then we have a square root. That's the idea of standard deviation. So for population, we are asked to find mean and standard deviation. Two parameters are two most important ones that we almost always find in population. Why do we need a variance? Because it's almost the same as variance. It's not exactly the same, but they are basically the same. Why do we need to use a variance and standard deviation, both of them? It's convenient to find the variance first, and then we have a square root to find the standard deviation. It's a kind of a tool that we calculate variance first to find standard deviation. It's a kind of tool, nice tool. So let's move on to the sample. We pick a part of population and it becomes a sample. So out of 1 million students, the sample size is 1 million, and let's pick 1,000 students. Okay. So this is first sample. This is sample 1. And notice that we could have another sample. So 1,000, another 1,000, and then we have a sample 2. Sample 2. So we put 1,000 back and we pick another 1,000. So every time we have a new sample, and these values could be different. Most of the time they are different. So at first, what is the sample size for this example? Okay, and this is 1,000. We chose 1,000 students out of 1 million. And then sample mean, symbol is X bar. And how do we calculate, how do you define the sample mean? Okay, same as population. The only difference is sample size. This is 1,000. Okay, so we divide it by 1,000. However, this is 1 million. Okay, the small n represents sample size. So if you have a first sample, so it could be some number. Let's just say this is a 3. And the second sample mean could be different. It could be 2. And for the sample 3, it could be 4. So every time we have a new sample mean could be different. So whenever you see sample in statistics, we need to see it as a variable. Because we change sample, we keep getting samples from the population, so sample mean could be different. So when you have a new sample. So that is one of the most important things that we need to know about samples. Sample variance is similar to population variance. And symbol is S squared. So numerator is the same. The only difference is this is the sample size 1,000. And when this sample mean is 3, then this is 3, 3, 3. And so the first one is, let's say this is 4, 5, or 2. Then, so we have 4 minus 3 squared, 5 minus 3 squared, 2 minus 3 squared. The same. That is very different from population variance. And we divide it by 1,000 minus 1. Okay? We are using n minus 1, not 1,000, but 999. Why do you subtract 1 from the n? Why is it? A lot of students, a lot of teachers are asking this question for years. And there are a lot of questions in the internet and asking for the reason why. So there is a rigorous mathematics, but I will wait until you feel comfortable with mathematics in statistics. So I will give you conceptual ideas. The sample is variable. So every time we have a new sample variance could be different. Let's just say sample variance for the first sample is 2. And this is sample 1, and sample 2. Sample 2, this is a 3, sample 3, and this is 2, or it could be 1. And we have a lot of samples, and we have a lot of sample variances. So the purpose of getting samples is we estimate population. From the sample variance, we want to estimate the population variance. That is the purpose. But sample variance is a variable. They could be different for every sample. Therefore, we have a mean value of sample variance. Mean of sample variance is a constant. There will be one number. So mean of sample variance should be the same as population variance. If this number is 2, then sample variance cannot be 2 because there are a lot of numbers for sample variances. However, mean of sample variance should be equal to sample variance. That's the purpose of sample variance. When we have an n or 1,000 for this example, and this is not, mean of sample variance is not equal to population variance. There is a mathematical derivation. When this denominator is n minus 1 or 999, then it is exactly the same as population variance. Mean of sample variance must be the same as the population varies. That's the reason why we should have an n-1. So rigorous definition and rigorous derivation will be given maybe in chapter 4 or 5. So please wait until we feel comfortable with a lot of concepts in statistics. So this is the conceptual ideas why we should have an n-1. The purpose of samples is to estimate population. So this is a mathematical definition of sample variance, and we still have n-1 and with sigma notation. Next, sample standard deviation, same as population standard deviation. We have a square root of sample variance. Okay? So it's easier to find sample variance first, and then we have sample standard deviation. Okay, I would like to emphasize that whenever you see population in statistics, notice that they are constants. They are fixed, they don't change. Okay? One number for sample size, one number for population mean. Let's say this is a 3.5 and it's a fixed one number. And same thing, this is a 2.5, then this is a fixed square root of 2.5. So there is only one number for each parameter, the population parameter. However, whenever we have a samples and you see it as variable, so they change every time we pick a new sample. All right? Okay, and this is a definition of sample mean again, and sum over observations. So previous example, we chose 1,000 students out of 1 million, and we have a sum over 1,000 observations so that it becomes only one number. Okay. And 1,000 numbers, and it gives us a number, let's say 3.5 for sample mean. And AP score, the sample mean is 3.5 because we divide by n or 1,000. And this is a mathematical notation or mathematical definition of sample mean. Okay, let's take an example. And there are 10 engineers and their annual incomes. So let's find the sample mean that a lot of engineers out there, and we chose only 10 engineers. And what is the sample mean of their annual incomes? Okay, X bar equals this number. Okay. I think they get paid more, way more than 50,000 these days. Okay. However, we have a new engineer or new person with a huge amount of salary. We have only one data point change. However, what's happening to the sample mean? Sample mean is this number. It's a huge, so it has a big change, only because of one engineer. So mean value gets easily affected by extreme value, and we are saying mean is not a resistant measure. It gets easily affected by the extreme values. So is there any other measure that is not affected by the extreme values very much? Yes, that is median. So median is simply midpoint of the data points. So let me show you an example to explain what median is. Let's just say there are two data points, 20 observations, and this is one sample. So mean value, the sample mean is like this. So how could you find the median? So we need to find the midpoint of the data points, 20 data points. So in order to find the midpoint, it's good to have a stem plot, because the stem plot rearranges these data points in ascending order from the smallest number to the greatest number. The smallest number is 5. So this is 0, 5, and first digit is 0, second one is 5. And let's just say, okay, this is the largest number, the greatest number, 8, 5. So stem has 0 through 8. Okay, 0, the first number is 0, the last number is 8, and this is stem. And let's find the second digit. So this is the smallest number, 0, 5. So this is the second digit. And next one is a 10, so 1, 0 over there. So likewise, we can put the 20 data points in the stem plot. Don't forget to find the key and pick any number. So let's pick 4, 5, and 4, 5 represents 45 minutes. And then we are done with the stem plot. So how could we find the median from the stem plot? We have 20 data points. We need to find the midpoint. So we divide it by 2, and this is 10. So we split 20 numbers, 10 and 10. So 10 to the left, 10 to the right. The midpoint is, to be precise, 10.5, because we have 10 numbers to the left, 10 numbers to the right. Let's count the 10 numbers from the first one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 10th data point, and this is 11th data point. To be precise, the midpoint is 10.5. So there's no data point at 10.5. So we need to have these two numbers, 10th data point, which is 20, and 11th data point, 25. The 20 and 25 divided by 2. So we have this number as midpoint or median. Okay? When you have even data points, we need to have two numbers, 10th, this is not the one, so 10th and 11th data points, and then we divide by 2. So let's find the median for these two sets of data. The first, there are 10 data points, so the midpoint is at 5 and 6, between 5 and 6. 1, 2, 3, 4, 5, right there. Okay, this is a 6. Therefore, 45 plus 50 divided by 2. This is 95 divided by 2. Therefore, this is 47.5. This is the median. For the second data set, and we have different data point for the last one, but the rest of them are the same. So 1, 2, 3, 4, 5, and 5th and 6th data points are exactly the same. 45 plus 50, therefore, this is the same as the previous one. For this example, median values are exactly the same, even though we have a different data point for the last one. So median didn't get affected by the extreme value. The median is a resistant measure. It does not get easily affected by the extreme values. So this is summary of mean and median. So when distribution is symmetric, the mean and median are almost the same. When it's perfectly symmetric, they are exactly the same. However, when it's skewed, mean follows the outliers. Mean is a kind of mean. They betray us, and then this mean value follows an outlier. Okay, you can remember it this way. Okay. Next, there is another tool for the center, and that is mode. Okay. The most frequently happening data point, that is a mode. So what's happening so most frequently? So in this example, okay, 13, 13, 13, see, it's happening 4 times. Therefore, mode is 14. Example 2. So what's happening most frequently? So 13, 13, and 13, 3 times. However, 8 is happening 3 times. Okay. Therefore, which one is mode? Both 8 and 13. So we are saying 8 and 13, this distribution is bimodal because there are 2 modes. Okay, 2 numbers are equally frequently happening. How about this graph? So which one is mode? Okay, mode is data point that is most frequently happening. Therefore, this is mode. The height or y value represents frequency. Therefore, this is mode. Okay. So this is mode globally. However, locally, if you just take a look at this local area, then this is a peak and this is a mode for this area. So this is a kind of mode, and we are saying this is major mode, like a major league. So major mode, and this is the minor mode. Okay. So, and we also say this distribution is bimodal. Okay. One is higher than the other, however, so this is called a bimodal distribution. Okay. This is a summary with the graphs. And when the distribution is symmetric, mean, median, and mode, they are at the same place. When it is left skewed, the mode is easy, the peak, left skewed or negatively skewed. So we describe the same thing with the two different expressions. So left skewed or negatively skewed, because it's pulled to the left or in a negative direction. So peak is mode, this is the mode, and which one is following the outlier? Mean or median? Yes, mean. Median is near the mode. It does not get affected easily, so mean follows the outlier. Positively skewed or right skewed distribution, and peak is a mode, and mean is following the outlier to the right. So this is the mean and median. So for AP test, they always ask this kind of question with single mode distribution. So this is always true with a single mode distribution. However, sometimes this is misleading students, because when you have a bimodal distribution, and things could be different. So notice that mean is following the outlier, and this is the left skewed. So mean is following the outlier, and median is following the mode, the peak. If we have another peak right there, then median is also following to the left. Okay. Mean is following to the left, is following the outlier, and median is also following to the left, it's following the mode. So it is possible. And mode is a peak, and median is near the mode, so mid is to the left. So mean is to the right. So even though this is a left skewed, and median shows first. So when we have two modes, and median could be moved to the left. So when it's a left skewed. So, and this is the bimodal distribution, but as far as I know, an AP test does not ask this kind of question because they don't want to confuse the students. You don't have to worry about it. But this is also possible. So I don't want to say that the mean is always following the outlier. So median always shows up first. It's not always true for this case. This is kind of exception. Okay. Next, interquartile, range. So we know how to find the median, and quartiles are medians of median. And Q1 and Q2 and Q3 IQR, I would like to show you how to find those medians with an example. That is much easier and faster. So let's use the same example, and there are 20 data points, and we rearrange them from the smallest number to the greatest number, and then we find median first. So median is right there, and between 20 and 25, this number is 22.5. So this is median right there, between 20 and 25. So it cuts the entire data set in half. So these 10 data points, and we can also find the midpoint over there, median of the first half. So this is between 15 and 15. So 15 plus 15 divided by 2, it's still 15. So let's just say this is Q1. The second half, there are 10 points, 10 data points, and we find the median again. So 40 and 45, we find the midpoint of 40 and 45, which is 42.5. This is Q3. Then what is Q2? Yes, median is Q2. So Q1, Q2, Q3, they are all medians. how do you find IQR? Q3 minus Q1, this is definition. We plug in numbers for Q1 and Q3, so we get this number. The purpose of defining IQR is we want to define outliers. So let's take one more example. So what if we have 19 data points? So all the data points. Then this is easier than the previous one because so 19 plus 1 divided by 2, and this data point is exactly median. So this is 20 divided by 2, and this is 10. Okay, and 10th data point is median. Okay, and we count, so don't forget to rearrange them first, and then we count the 10 data points right there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is exactly median. Good. And then, so how can you find the Q1? So you should be careful of counting this point. Do we include median or do we not include median to find the Q1? The answer is no. Okay. So this is the median, and we do not include the median, and there are 10 data points, not 11. 10 data points, and then we find the midpoint, the median, and this is Q1. So be careful of this median point, and we should not include this point, and we get the rest of the data to the right, and there are 10 data points, and this is another midpoint. This is Q3. Good. So Q3 minus Q1, this is IQR, and then we get IQR like this. So be careful of median. We do not include median for Q1 and Q3. So how could you define the outlier with the IQR? So we multiply the IQR by 1.5. And idea is like this. So we have median Q2, and we have a Q1, Q3, and this is Q1. We go to the right by 1.5 IQR plus Q3. From Q3, we go to the right by 1.5 times IQR, and then we make a boundary right there. So everything beyond this boundary is outlier. So same thing to Q1. So we go to the left by 1.5 times IQR from Q1, and we make a boundary for outliers, and everything before this boundary is outlier. So this is the idea, and this is definition of outliers. So we know the definition, and we just plug in numbers, and we find the outliers. So from the previous example, we found Q1 and Q3 and IQR. We already found them. So we multiplied IQR by 1.5, and we get this number. So we subtract 1.5 times IQR from Q1, and we get this boundary, negative 26. This is negative 26.25. And we add 1.5 IQR to Q3. So this is 83. This is 83.75. So let's find out the data points in this boundary region. Before 0.5, and there's nothing. So there's no outlier before 0.5. So after this boundary, beyond this boundary, we have 85. Because the boundary is 83.75, and 85 is right there. So we have one outlier in this data set. So we know the definition, we just follow the definition, and we can find the outliers like that. So in order to describe the distribution, we usually use 5 numbers: minimum, Q1, Q2, Q3, and maximum. And so we can visualize it with a box plot. So what is a box plot? Full name of box plot is box, whisker, and dot plot. So what is a whisker? Okay, and this is rabbit. All right. All right, this is rabbit, and so this is a whisker. It's a strong string. And this is a whisker. And why do you use a whisker? So you will see it in the example. And we use a single points for the outliers. Let me give you an example. So same example, and we got 5 numbers: minimum, Q1, Q2, Q3, and maximum. So Q1, Q2, Q3, let's use a box for these 3 numbers. So right there. So this is a box, and each segment represents, the first segment represents Q1, the second one, M, the third one, Q3. So this box represents Q1, Q2, Q3. And we have a boundary for outliers. So boundary is like this, right there, and negative 26 and positive 83. So positive 83 is somewhere here. And we have these numbers beyond the Q3, but below the outliers boundary, and we are using these data points, and we represent these data points with a whisker. Okay, so outside the Q3 and inside the outliers boundary, and we use a whisker. Okay, right there. And then, so 85 is an outlier, we use a dot point. So we can clearly see, oh, this is an outlier. Okay, this is the idea of a whisker and box. Same thing. And lower boundary of outlier is negative 26. Negative 26 is way over there. So these data points are represented by the whisker. So this is a 5 right there. This is a 5. And whisker represents the data points between Q1 and the lower boundary of outlier. Okay. This is the box. This is the box plot. So spread, how do you describe the spread of a distribution? And we use, we may use a standard deviation. So in order to find the standard deviation, we need to know deviation first. So what is deviation? Deviation is, this is sample mean, and data point. Data point, this is the first data point right there. And data point minus sample mean. Okay, 1 minus sample mean, and this is negative 4. This is deviation. So we define the deviation first, and then we find the standard deviation. So let's practice one more with data point 8. This is 8, and sample mean is 5. So 8 minus 5, and that is 3. And this is a positive deviation, and this is negative deviation. So observation, usually we use xi minus sample mean x bar. So this is deviation. So let's find standard deviation with this data set. When we are dealing with a data set, we should know if this is a population or sample. Depending on the data set, and calculation is different. The mean value is the same, however, standard deviation or variance are different. So we should be very careful of what we are dealing with. What is it then? I don't know. So I assume that this is population and sample, and I solve, I find the statistics, assuming that this is a population and sample. So let's assume that this is a population, then population size is big N, and it is 9. And population mean, so we add all those data points numbers, and then divided by 9. Okay, which is 5. Notice that we are using these symbols. The population means mu most of the time. And population variance, sigma squared. So how can you find the population variance? So I would like to show you every step of every point. First, this is the first data point, and 1 minus sample mean 5. Okay, our population mean 5, and 1 minus 5 and negative 4. This is deviation, and then we square it. So that it becomes a positive. Next data point, 3. So this is individual data point 3 minus, and population mean 5, and this is negative 2, and we squared it, and it is 4. So likewise, we can do the rest of the data points. So deviations could be positive and negative. And we square them, they are all positive, of course. So if we have a sum over these 9 data points, what is it? It's a 0. It looks like deviation is a 0, but it is not true. Each data point has a deviation. Sum over all deviations is a 0. So that's why we need to square it, make negative numbers into positive. So, and squared deviation is this, 52. Okay. So with this number, we can calculate variance. We divide this number by 9, so this is a variance, population variance. So how about the population standard deviation? So this is the variance, and this is square root of 5.78. Good. So I assume that this data set is a population. However, if this is just a sample of a big population, so let's say there are 1 million students, we chose only 9 students, and they have these data points, then now this is a sample, so sample size is 9. And sample mean is x bar, and so we add all those numbers up and then divide it by 9, and it is 5. Same as this number. And then sample variance is different. This is a squared deviation, and then we need to divide it by 9 minus 1, 8. So s squared, and we divide it by 8, and then we get this number. So we have a square root over it, and this is sample standard deviation. So notice that we have a new sample that is different from this sample. So these numbers, this is the same, this is the same. These numbers could be all different. The population does not change, but if this is a sample, then these numbers could be different. So this is kind of summary, and center we use, in order to describe the center of distribution, we use mean and median. And spread is the maximum data point minus minimum data point. And this is max, and this is the mean. Then the spread is telling us how wide this distribution is. However, for some distributions, they don't have max or min. So it goes to positive infinity and it goes to the negative infinity. So range is infinity. In that case, so we cannot find the range. Instead, we have standard deviation. Okay. Or we have interquartile range. Next. So distribution is given, so you are asked to describe the distribution. And it's a little bit vague. So what do you need to show in our FRQ? So they ask you to describe the distribution, and all right, there are a lot of things we can say about a distribution. So I give you some directions. You need to show the shape of distribution and center, spread, and outliers. Okay. So in short, you remember it as SOCS, SOCS, and 4 elements of a distribution. But let me show you an example. The data set is given. It's better to have a distribution like this, like that. So SOC, S. At first, shape. Is it symmetric or is it skewed? Yeah, it looks skewed to the left. So show left skewed. And it's good to add clusters. Okay, there are 3 groups of data points. in this distribution. So there are 3 groups. They are not connected. They are separate. There are 3 groups. So 3 clusters. And next, median. Median is 28. You can count the data points and then find the median. You could also say mean for this distribution. So spread, see this is the minimum and this is the maximum. All right, 333 max minus 14, and we get the spread. So outliers, use the definition of outliers, and you'll find 14 and 18, they are outliers. So you'll be good if you show SOCS. I think this is a good example for an FRQ. All right, I'm done with this lesson, and next chapter we are going to learn what the normal distribution is. This is a great function for statistics. Thank you for watching.